Good afternoon, everybody. Welcome to lecture. Today we're going to be talking a little bit more about IR spectroscopy, finishing that up, doing a few practice problems. Then we're going to move on to NMR spectroscopy, which is a new kind of spectroscopy. It's extremely powerful, gives you detailed structural information. But first, let's take a look at the survey question that we had from last time. So remember, these are things, quizzes in Canvas that you can do from the point at which a lecture ends until the next lecture finishes. You've got a big period of a couple of days to work on them, where basically you just enter an answer. Whatever answer you think is right doesn't have to be completely right because you get credit for just participating. But this one wanted to know what molecule gave an IR spectrum that looks like this. So this is an IR spectrum, and we're fairly new at interpreting these. So at first glance, this is a little bit overwhelming. I mean, there's peaks everywhere, and these structures look a little bit complicated. But let's just break it down and try to see if we can pick out the really important things and get past the noise, essentially. So remember, IR spectroscopy, we're just focusing on the functional group region, the 1500 to 4000 region. So while the fingerprint region, which is this region below 1500, is got a lot of peaks in it, and it's got valuable information, we can't really get anything out of it, so we're just going to ignore that. So we've got peaks here, 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 some peaks over here and there that we can try to figure out what they are. And there's a big hint here in terms of the big peak here at 1752 wave numbers, inverse centimeters. So if you take a look at your table and you try to find something that matches well, that looks like a C double bond O of an ester. And that's just, because they're really strong, they're in this region. It's probably not a ketone or an aldehyde or a carboxylic acid, because those have frequencies that are lower, like 1710. But 1752 seems like ester. So if you look at this table, that's a ketone, that's a ketone. Those aren't going to be good choices. Here we have ester, ester, ester. So 3 esters, but one of the esters doesn't make sense. This ester down here, E, doesn't make sense because the C double bond O is conjugated. It follows this double bond, double bond pattern that we talked about defining conjugation previously. That means that the frequency of the carbonyl in that molecule will be lower. It wouldn't be at 1752, it would be lower. So it's probably not E. And then there's a couple other things that you can look at as well. In addition to the ester peak, the C double bond O peak, I can see something that looks like about a peak at 1500 and something near 1600. These are peaks that are characteristic of the CC bonds in an aromatic ring. So if you're comfortable with that, if you're used to looking at those, this is telling you should probably be on the lookout for an aromatic ring. And C and E both have aromatic rings, but D does not. So it's probably not D, because D doesn't have the right functional group to match the peaks we're seeing in the spectrum. Then if you take a look at what's going on around 3000 or so, if you draw an imaginary line up at 3000 straight up, what you see is there's signal on the right side of 3000, just below 3000. That's characteristic of CHs where the carbon is sp3 hybridized. That would be alkyl type pieces. And structure D has those, but again, D doesn't fit because it doesn't have aromatic ring in it, but C does. C has CHs of the sp3 hybridized type there and there. So that seems good. Then when you look at the other part of this clump, there's signal that's greater than 3000 appears just to the left of 3000. So those are characteristic of sp2 hybridized carbon H's. So that's probably telling us we've got carbon-carbon double bonds here attached to an H, and those could be in an aromatic ring, like we have options for, or could be alkene. And again, this option C has got CHs on sp2 hybridized carbons, so that looks like it's consistent. And then finally, there's this thing at 3500, which if you weren't savvy enough to, if you didn't realize that this is a carbonyl overtone, you might mistake this for an NH or an OH, but it isn't any of those. It's just the overtone from the very strong carbonyl peak of the ester. So this looks like, when you compare all of the data, the one it fits the best with is C. And let's see how the class did on this. I'm going to submit this quiz, and what that's going to do is pop up the solution that explains the data. So the solution that I put up here, and I'll make it just a little bigger, summarizes all this stuff that I was talking about. It's saying there's aromatic C double bond C signals here. There's an absorption for the ester carbonyl there at 1752. There's sp3 hybridized CHs and sp2 hybridized CHs on either side of 3000. There's a carbonyl overtone. And then one thing that I didn't mention, but if you were looking for it, you would probably see it, is there's even a CO single bond that you can pick out of the fingerprint region. It's a very strong peak. So it's, those things, when you put it all together, this is the molecule it must be because it matches. It's the only one that has all the right features to match this spectrum. And it'll take you a little while to sort through this with your table and things and just getting familiar with where the peaks are. But once you get some practice with it, it'll go much, much quicker. So let's see how the class did on this one. I'm going to look at the survey statistics here and see how people did. Well, it's good. It was the most popular answer, for sure. There was a lot of variation in answers, obviously. They're kind of all over the place, but at least more people picked C than any other answer. And if you picked one of these others, you probably recognized something like a characteristic of one of the molecules. You just probably didn't get it all at once. You have to kind of put all the data together at once. The peaks are telling you a lot of different things about different functional groups in the molecule. This molecule has many different functional groups, but they're all you all have to try to make them all consistent at once. So the molecule has to contain a non-conjugated ester and an aromatic ring and sp3 hybridized groups somewhere. And this is the only one that does all of that. All right. Any questions about that? All right, I want to do a couple of announcements. So let's talk about some ALEX stuff. So there's an ALEX homework 1 assignment for lecture that's due on Friday. That covers spectroscopy A and B, so mass spectrometry, IR spectroscopy, and hopefully you can get through all those problems now, and I'm going to work through a few practice problems here. And then the homework 2 is now open also. That covers spectroscopy C, the first part of spectroscopy C, which is NMR, nuclear magnetic resonance spectroscopy, which we're going to start talking about today. Another thing I want to do is give you a molecule of the day. So we're going to do this occasionally, like not every day, but on some days, I'm going to introduce a molecule of the day, and these are just molecules that are interesting. They may have some structural features that fit with the lecture material we're talking about. Maybe they're in the news. Maybe they've got some important function that I want to highlight, or maybe they're just interesting. But this one is called cinnamaldehyde. And as the name kind of suggests, this is a molecule that's present in cinnamon bark. It's what makes cinnamon smell and taste like cinnamon. So if you're into the cinnamon flavored drinks and things, or you like it as a spice that you sprinkle on whatever, you can thank this molecule for giving cinnamon its characteristic odor. It has a bunch of different functional groups in it. It has an aromatic ring, it has a CC double bond, and it has an aldehyde. What we would see in the IR spectrum for this molecule is all of those things. We would see the CC double bonds of the aromatic ring appearing at 1500, 1600, either one or the other or both. If a molecule has an aromatic ring, you may see one of those characteristic peaks, you may see the other, you may see both. Sometimes they're weak, sometimes they're strong, but those are the ones to look for. This would give a peak in the alkene region, which is just a little higher frequency than the 15 and 1600s. There would be an aldehyde carbonyl C double bond O, but this would be a conjugated C double bond O because it goes double bond, single bond, double bond. So whereas a normal aldehyde carbonyl would be more like 1710 inverse centimeters wave numbers, this one would be lowered from the usual 1710 to maybe about 1685 or 1690 inverse wave numbers due to conjugation. And then the other thing it would have is it would have these characteristic peaks for CH, and this is a special aldehyde sort of bond that you don't see in any other molecule. sp2 hybridized carbonyl carbon bonded to an H. This usually shows up as two peaks, about 2720 and about 2820 inverse centimeters. So when you see the carbonyl lowered due to conjugation and you see those characteristic aldehyde peaks, you know you're dealing with a conjugated aldehyde. And that's some of the things that you might see if you stuck cinnamaldehyde in an IR spectrometer. So that's our molecule of the day. The way that these are going to function is you'll see these on an exam. There's going to be 5 of them on the first exam, and it'll just be picking the molecule out of a lineup and matching it up with its name and function. So what you'll see on an exam is a structure of cinnamaldehyde with a letter or a box below it, and then you'll see a bunch of names and characteristics listed in a list A, B, C, D, and it would say cinnamaldehyde compound found in cinnamon, something like that, and then you just have to match it. Usually the structures are going to be different enough that it's pretty easy to keep track of them, so hopefully you find that exercise an easy way to get points and start developing your pattern recognition skills, looking for functional groups and arrangements of functional groups that have particular functions. So that's molecule of the day. And then I want to go and talk about some IR practice problems too, just to go through a few and highlight some strategies for solving these things. I'm going to load up a PowerPoint file here. And the PowerPoint file is one you can download off of Canvas, and you can play it like I'm going to play it here so that you can sort of follow along step by step with the analysis. And there's no real right or wrong way to approach this. You just essentially have to look at the functional groups and figure out what all the peaks are. This is a strategy that I'm going to use. I'm going to show you a step-by-step method for analyzing this molecule. So this is an IR spectrum of something. The functional group region shows a big peak here, big signal there, and a little signal there. So I would get my table in front of me, and I would look at this thing, and the first thing I would do is figure out where is that really big peak. And when you look at the x-axis here, you can see it's at 1710. Sometimes you're told exactly where the peak is. Sometimes you have to look at the x-axis and try to estimate where it is. But the frequency is important because it can distinguish between aldehydes, ketones, and esters. So this is a ketone or aldehyde or carboxylic acid carbonyl based on its frequency. But we can figure out which of those three is most likely based on the other things that are present in the molecule, in the spectrum. So the other things that are here, there's also a C double bond overtone, which is common, so don't confuse that for an OH or an NH. It's just a part of the C double bond O. Then what I usually do with these spectra is to draw a line up from 3000 vertically and look to see is there signal on the right side of it or the left side or both. So this one has signal on the right side, which is just below 3000. That's characteristic of sp3 hybridized CH bonds. But it doesn't have really anything substantial on the left side. There's no peaks appearing over here, which means it probably doesn't have sp2 hybridized CH bonds. So maybe there's no double bonds in this molecule. Maybe it's just alkyl groups. Those are the things you can learn from the spectrum, and that's about it. You can't figure out exactly what molecule this is based on this IR spectrum, but what you can do is you can narrow it down and you can say, when you consider, okay, these are all the things that I've identified for functional groups, this is probably a molecule that's a ketone that has alkyl groups, R groups on either side. And I'm sure it's not an aldehyde because it doesn't have the characteristic 2720 and 2820 peaks that an aldehyde would have. It also doesn't have a gigantic OH peak, which is what a carboxylic acid would have. So it's probably a ketone that's just got alkyl groups on it. And that's the best you can do with this spectrum. That's what you can learn from the IR spectrum. Let's look at another example. Here's another spectrum that's got some peaks on it. And again, in the functional group region, we're just interested in from 1500 on. We've got a big peak here. peak there, bunch of peaks here, something there. If we identify where the carbonyl is by looking at the x-axis, 1710, so that's about like what we had in the previous example. It's probably an aldehyde, ketone, or carboxylic acid just based on the frequency of that peak. There's also an overtone over here that you can see, and that's what's I'm going to highlight next. And then there's some other signals too. Let's take a look and see what else we've got. This is one where we are seeing this characteristic CH that an aldehyde has that a ketone does not and a carboxylic acid does not. So the fact that we're seeing a 2720, and that one stands out really strongly because it's quite a bit different than the sp3 hybridized CHs. We're also getting a 2820, but a lot of times that's buried in the signal for the CHs of the sp3 hybridized type. So it's not always possible to get the 2820 definitively, but the 2720 is usually really distinctive. Then if we draw the line up at 3000 again and look for signal on just to the right of it, I can see sp3 hybridized CHs. And then on the other side, I see no signal just a little bit above 3000, so it probably doesn't have sp2 hybridized CHs. So this is a molecule, we put it all together, it's an aldehyde. This is the major functional group, and it's got an alkyl group of some sort on it. That's what I would predict for this spectrum. And that's what you can learn about this molecule from this spectrum. Next, I'll take a look at this other one here. Again, functional group region is where we want to look. We've got a big signal here. There's a C double bond O at the 1755, and I know it's a C double bond O of an ester specifically because it's got this higher frequency than is typical for aldehyde, ketone, or carboxylic acid. So knowing that the frequency is higher tells you, hey, I've got an ester. And then what else is in the molecule? There's not a whole lot. There's a tiny little overtone, which is usually what you see when you have a carbonyl. You get the overtone, which is about twice the fundamental frequency. And then, look at that. If you were looking in the fingerprint region, you can see there's a really big CO peak here that you can pick out, and esters usually display that. So you're not required to pick that one out of the fingerprint region. It's sometimes hard to get stuff out of the fingerprint region, but CO is like the one signal, the one absorption that you can usually see. So that's helpful. That's also suggesting ester. And then finally, the region at 3000, there's signal on the sp3 side of things. So it's a CH, incorporates CHs of the sp3 hybridized type. So this is an ester that's just got alkyl groups attached. So the structure is something like this. This is the major functional group. It's got an ester, and the two R groups here are alkyl. One last example. All right, this one's kind of busy. By the way, these are all real spectra. I got these out of a database there where somebody actually did the experiment and collected the data and published it in a database. And this one's got a bunch of signal here. We can see there's from 1500 on to 4000. There does look like there's something at 1500 and maybe something at 1600, although it's small. We've got some things over here that we're not sure what they are. And then we've got some big signal here, big signal there, and a really big signal there that's broad and smooth and very strong. And that's what strikes me right away as I see that, and I think alcohol OH. So this has got an OH group in it. It's an alcohol. It's got a hydroxyl group. Then I'm also picking up C double bond C aromatic. It's not as strong and doesn't kind of knock you over like the alcohol does, but you know, we start getting used to looking at around 1500 and around 1600, we'll start to see these things. So this is probably a molecule that incorporates both an alcohol and an aromatic ring. What else has it got? If we look at the 3000 area, we've got sp2 hybridized CHs and sp3 hybridized CHs. So it has both types. These are the H's that are attached to probably the aromatic ring, and these are H's that are attached to C's that aren't part of the aromatic ring, that are part of an alkyl group. And you might be wondering, well, what's some of this? What's this stuff up here? It's in the region of of the aromatic of where you see carbonyls, but these are way too small to be C double bond O's, so you can just ignore them. They're from other vibrations that are occurring that are kind of more complicated than the ones we're studying. So they're kind of too small to worry about. So I would say just ignore them. We're just going to go for the big absorptions. And what this tells you is it gives you a list of functional groups that are in a molecule. This molecule has an OH. It has some kind of benzene ring, and it's got some kind of R group where the R is alkyl. And so it's an alcohol with aromatic ring and alkyl group or groups. Yeah, what do you got, Cole?
If there was two aromatic rings, how would that look?
It would look basically the same. You might see multiple peaks for when you have multiple functional groups. You sometimes see two peaks for each one if they're different enough. So like if you have two carbonyl groups in your molecule and one is a ketone and one is an ester, they might be separated by enough room that you might see two peaks. But if you got two ketones, you're likely to just see one peak, and they kind of overlap and give the same absorption, what appears to be the same absorption. So you may or may not see different numbers of peaks. It's a good question. I would just say that when you see an IR spectrum and you see OH, it probably start with the simplest example, like it might be one, and later on you'll have other spectral information that might suggest whether you have two or more. So, but for most examples, it's just going to be simple molecules that have like one or two functional groups. So that's a good question. All right, well, that is that. So any questions about these IR spectra? Yeah, what do you got?
What would the absorbance difference be between like a small and medium peak and something that doesn't count as a peak?
Right. How small is small enough to ignore? I guess it's a good question. It's one of the things about IR spectroscopy that's a little bit challenging is that that there's a lot of peaks, and sometimes they're big and they're obviously important, like the OH, and sometimes they're small enough that you wonder if you should even pay attention to them. So this peak at 1600, normally I wouldn't consider that to be strong enough, but I suspect that there's an aromatic ring because I'm seeing a strong peak at 1500, and I'm also seeing these sp2 hybridized CHs, which could well come from an aromatic ring. So I have other evidence to suggest that maybe there's an aromatic ring. So I'm more likely to look at this peak and say, yeah, that's probably a C double bond C aromatic type absorption. So yeah, it's hard to know for sure whether to look at it or not. But one of the things I do know about C double bond O's is that they're supposed to be very strong. So the fact that these are weak means it's more likely that I'm just going to be able to just ignore them, because that's not what they're from. They're from a bending motion of the molecule. Yeah, lots of peaks. I mean, they don't always appear exactly in one spot, so you just have to do the best you can with it. Try to assign them as best you can, and what we're going to see is that you're going to have other data besides IR spectroscopy to help you analyze molecules. We have mass spectrometry, but now we're going to be moving in and talking about another kind of spectroscopy, NMR spectroscopy, nuclear magnetic resonance spectroscopy, and that provides a lot more kind of definitive data. There's a lot less sort of speculation with NMR. It contains a lot of embedded detailed information that's a little easier to extract. There's fewer peaks that you can just ignore. It's like in NMR, you should be able to figure out basically every single peak, and that's what we're going to talk about now. So, right. So I'll introduce this NMR spectroscopy concept. This is the chapter in the textbook labeled Spectroscopy C. Spectroscopy Part C. And the full title is Nuclear Magnetic Resonance. Spectroscopy. Spectroscopy. And for short, it gets abbreviated NMR. And by the end of the lecture, hopefully it'll make sense why we're calling it that, why it has that abbreviation. It's about nuclear states in an atom. It's about the magnetic properties of nuclei and this concept of resonance, which we'll explain in some detail. So NMR it studies the magnetic properties of nuclei. Magnetic properties of nuclei. Some nuclei are magnetically active. In other words, they behave as though they were magnets, little magnets. It has to do with the number of protons and neutrons in a molecule, but if a molecule has either an odd atomic number or an odd total mass when you add up protons and neutrons, then it will be magnetically active. In other words, it'll behave like a small magnet. So some nuclei have a property called spin. So I'll say some nuclei have a property called spin and behave like tiny magnets. So proton is one of those nuclei. Proton, that's hydrogen with one atomic number 1 and no neutron. So this is essentially what it is. It's a hydrogen nucleus with a proton and no neutron. This atom has spin, and it behaves like a tiny magnet. So these atoms that have spin, they're kind of like balls of spinning charge, and that spin creates a magnetic moment, which then we can manipulate with an external magnetic field. So proton, which is the most common isotope of hydrogen, that's one that's magnetically active, and we can study by this technique called NMR. So essentially, this is a good technique for looking at protons in molecules. And organic molecules are full of protons. They're covered in protons. They like wear a proton skin. So they are going to be nice to study using this technique. I've got to see what happened here with my... Good, I think we're still recording. It went dark on me all of a sudden. Okay, let's talk about how this works and what you can learn about a nucleus by sticking it in a magnetic field. I'm going to take this opportunity to keep the computer awake. Just launching an app that keeps it from sleeping, so hopefully it won't go to sleep on me. I'm going to re-aim the camera a bit here. Normal tracking. There we go. Okay. So here's the situation. You have a little ball of spinning charge. This is our proton. It's got a positive charge, and it spins, and that creates a magnetic moment where this arrow that I'm drawing on the spinning ball of charge is indicating the direction of a magnetic moment. It's like the poles of a magnet. If you've ever played with a bar magnet, and hopefully you have, you'll notice it's got a north pole and a south pole. So this is kind of like the north pole up here, and this is like the south pole of the small, tiny proton magnet. So they're all like this, and when you put the proton in an external magnetic field, you can influence it. So this is proton. And then what I'm going to do here is use the textbook kind of strategy for indicating what an external magnetic field might look like. So this represents the direction of an external magnetic field that's indicated by this symbol B0, B0, and it's just saying we're gonna put this little magnet inside of a big magnet. So imagine having a little bar magnet and then sticking a giant magnet next to it. They influence each other. The North Pole here and the North Pole here in this picture are aligned. That's one way that this atom could exist. And it turns out when you put atoms, protons, in a magnetic field, there's two ways that they can align. They can either align with the external applied field. So I'm going to say this is a strong external magnet. And it has a direction. It has a north pole and a south pole. Proton can either align with the magnetic field or it can oppose the magnetic field. In other words, it can look like this. So we have two different names for these different spin states. When it's up and aligned with the magnetic field, this is called the alpha spin state. Actually, what I think I want to do here is draw these flipped around. So bear with me for a minute. I'm going to switch the direction of these things because I want this one to be down here and I want this one to be up there. This is called the alpha spin state. It's aligned with the external field B0. Up here, this is called the beta spin state. It's opposed to B0. And if you're a little magnet and you're aligned with the big magnet, that's a lower energy state. The poles are lined up, so the fields aren't fighting each other. This is the lower energy state. And up here, where it's fighting the magnetic field, this is a higher energy state. And there's an energy gap between these two states. I'll draw a picture here. The way this is drawn is to indicate that the beta spin state is higher up in energy, the alpha is lower. And there's some energy gap between them. I'll call that delta E. That's the energy gap. It's equal to h nu, where h is Planck's constant and v is a frequency of radiation. It's called the resonance frequency. So you take protons, you put them in a strong magnetic field, and then you can irradiate them with radiation, electromagnetic radiation. And if you get the frequency of the radiation exactly matching the difference in energy between these two spin states, you can cause a flip in spin state. So I'm going to put this in words and saying that energy input can cause spin flipping between alpha and beta spin states when the frequency matches the energy gap. So when you find just the right frequency, you can cause spin flipping, and then that results in absorption of some radiation. So what NMR does is it irradiates a sample inside of a magnetic field with some radiation, and then some of it gets absorbed because it causes spin flips. And then what you see is a spectrum that shows you what radiation was absorbed and what wasn't absorbed. So, so it's a way of like looking at the energy gap in these atoms. So this frequency that causes the spin flipping is called the resonance frequencies. And there are a number of different factors that can affect the gap here between the energy states at alpha and beta. Every proton is different. Protons in different chemical environments have different resonance frequencies. So I want to put this down because this is a really important concept. Protons in different chemical environments have different energy gaps. And therefore different resonance frequencies. Different resonance frequencies. So the thing that makes them different is their electronic environment, what electrons are around them. So this is another big concept in NMR, is that the electrons around a proton, the electrons around a nucleus, affect its magnetic environment. I'll put a star next to this bullet point. Electrons around the nucleus shield it somewhat from the external applied field B naught. So when you have a proton, if it didn't have any electrons, it has a particular energy gap. You put some electrons around it, and that tends to oppose the external magnetic field, makes the gap a little smaller. So electrons around the nucleus shield it somewhat from B0 and lower the resonance frequency. So we're going to talk about two concepts, or maybe I should say terms. Shielding. Is due to electrons around the nucleus. If you're a proton in a very electron-rich environment, you have a lot of shielding. Protons in electron-rich environments have more shielding than those in electron-poor environments. So protons have different frequencies that they absorb at depending on what they're near. So imagine a proton is near an electronegative element, like a chlorine. The chlorine is an electronegative element. It has a hunger for electrons. It tends to suck electrons towards itself. It leaves whatever's near it electron deficient. A proton that's in that environment would have less shielding, and that affects its energy gap. So more electrons makes the energy gap smaller. Fewer electrons makes the energy gap bigger. So what I'm telling you is that protons absorb at different frequencies depending on what other atoms are nearby. So this is really going to be helpful because all protons have a distinctive signature that we can look at and take advantage of. So I'm going to cue up the projector again and put up some slides to talk about this. All right. Okay, so there's a new set of slides that I'm going to get from the Canvas page. So these are available for download on Canvas. Let's take a look at them. So first of all, we'll start with a NMR spectrometer, what it looks like. We have one of these upstairs on the 4th floor, and we'll get to see it pretty soon. Like one of the coming weeks, we'll take a tour or trip over there and we'll look at it and show you how it works. This is a pretty good picture of it, actually. There is a giant kind of thermos-like thing that sits on the ground. It's about this big around. It's about this tall, and it's got a superconducting coil of wire inside of it. So superconductors are super interesting because they have zero resistance. So this coil is sitting in a bath of liquid helium because it only works if it's very, very cold, which is at 4 degrees above absolute zero, 4 Kelvin. So I mean, it's a pretty extreme environment. So you put this superconducting wire in this extra cold bath of liquid helium, and then you can put a current into it, introduce a current, and the current just goes. It doesn't degrade because there's no resistance. That creates an electromagnetic field that then is the strong B0. That's the external magnetic field I'm talking about with this orange arrow that I've been drawing over here. So this magnet provides the external magnetic field. Then you stick a sample inside the heart of this beast and it goes down into this tube, down into a tube in there. This is showing the inside. So there's a small glass tube that we've got the samples in that sit in the belly of this extreme magnetic environment. Then there's a console that provides electronics and the radiation that we need to cause the spin flips. And then a computer to record the data. So what you get out is an NMR spectrum that looks something like this. I'm going to make this bigger. There we go. So these are some features of NMR spectrum. It's a graph. There is an x-axis, which goes usually from 0 to about 10 for proton NMR spectroscopy. There's on the y-axis, it's usually not labeled on the y-axis, but the y-axis is intensity. And then there are peaks, and the peaks go from the bottom up. There's the baseline, and there's a peak there, and then you go over here, and there's a peak here, and then you go over here, and there's a peak here. The units are in something called parts per million, and the thing to just know about that is that the usual range is 0 to 10, and we actually mark the 0 point with an external reference with a standard. Well, it's actually an internal standard that a lot of times gets put in. So there's a compound called tetramethylsilane, and tetramethylsilane, or TMS for short, is a reference compound that marks the 0 point of the spectrum. These protons on methyl groups that are attached to silicon are very shielded. So people put this into their material when they analyze it, and they find this peak, and they use that to mark the 0 point for the spectrum. And the ends of the spectrum, the right side and the left side, they have a couple of really important terms to get used to. The right side of the spectrum is the more shielded side. So over here are the electron-rich protons. The ones that are in electron-rich environments, they are well shielded because they have lots of electron density around them. This is also called upfield. So up is to the right and downfield is to the left. That's just going to be something you're going to have to get used to. Lower chemical shift. So 0 is very low chemical shift. 1 is higher, and all the way up to 10 is much higher chemical shift. Chemical shift is just a measure of what's the part per million value for that signal. These are the electron-rich protons. Then you got over here on the other side, this is the other neighborhood. This is the poor neighborhood, electron-poor neighborhood. This is called downfield. These protons aren't as fortunate. They just don't have as many electrons around them based on what they're near. Higher chemical shifts, these are electron-poor. So, and this is an example of a spectrum of a molecule called methyl tertiary butyl ether. We've talked about this one before, just briefly. It's got a methyl group attached to an oxygen, and then there's a tert-butyl group. So the tert-butyl group has a carbon that has 3 carbons attached to it. Each of those carbons is a methyl group, so it's 3 methyl groups attached there. And if you look at this molecule and you rotate it, you can see that the methyl groups on the tert-butyl are all the same. They all can be rotated into the positions of the other, so they are collectively the same as each other. So this is one kind of proton. So the protons on this methyl group are the same as each other, and they're identical to those protons and those protons. So this represents a clump of 9 identical protons. Over on this carbon, there's a methyl group. It's got 3 protons, but this methyl group isn't the same as these because they have different proximities to the electronegative oxygen. So oxygen is pulling electron density away from things that's nearby, so it has a big effect on that carbon. These H's are more electron poor because they're closer to the oxygen. That's why the signal for this methyl group appears here at about 3.2 parts per million, and the collective signals for these 3 methyl groups appears more at like 1.1 parts per million because they're more insulated from the oxygen because they're 1 carbon further away. So, and we're going to learn to recognize these part per million regions to be able to know when you see a signal at 3.2, hey, that's probably protons on a carbon that's next to an oxygen. And when we see protons in this 1.1 region, those are probably protons on carbons that are further away from oxygens. And you get 2 signals here. That's a signal and that's a signal. And then there's the signal from the internal standard, the TMS, which isn't part of this molecule, but just was added to mark the 0 point. That's a typical NMR spectrum. Any questions about that NMR spectrum? Okay, let's talk a little bit about chemical shift. So protons have different chemical shifts based on what they're nearby. This is the concept of like electron poor and electron rich. This table is one out of the textbook. I'm also going to give you this to use on exams. It's in the appendices that I provide for the lab. It's also in Canvas's reference materials. It's a good list to get comfortable using. You don't have to memorize it because you're going to have access to it all the time, but it's good to get some comfortable working knowledge and practice with it. And what it says is that it's arranged in order of increasing chemical shift. So the ones that appear on the far right side of the spectrum in the shielded region are the alkane type groups, alkyl groups. So sp3 carbon H's, they tend to be the most electron rich. They appear at 0.9 to 2, and specifically if you have methyl protons, they're at about 0.9. If you have CH2 protons in an alkyl group, they're about 1.3 or so. And if you have CH's, where it's a carbon attached to one H and 3 other carbons, it's a little higher in chemical shift, it's about 1.7. So this assumes that these are H's that aren't nearby any group that might steal some of their electrons away. But that's just characteristics. So alkyl groups tend to show up on the right side, the shielded side, the upfield side of the NMR spectrum. Then there are some structural features, functional groups, that impact that and have a de-shielding effect. They take electrons away and they remove shielding. So sometimes you'll hear this term de-shielded. That means stealing electron density away and making the nucleus appear further to the left at higher chemical shift, downfield. This is an example of one of those kinds of situations. So when you have a double bond in a molecule, CZ, where Z could either be carbon, oxygen, or nitrogen. So this could be a carbon-oxygen double bond, a carbonyl, or a carbon-carbon double bond, an alkene. But if you're a proton on a carbon that's next to one of those kinds of functional groups, it has a de-shielding effect. And as a result, you would show up at 1.5 to 2.5, so higher chemical shift. So when you see signals in that region, you can think, well, maybe these are protons that are near a double bond of some sort. Being attached directly to a triple bond causes a proton to show up at about 2.5 parts per million. This is one that's real common, and we're going to see these a lot, is if you're a proton on a carbon that's attached to an electronegative Z group. This would be a nitrogen, an oxygen, or a halogen. These are de-shielded even more, and it says 2.5 to 4. It depends on the electronegativity of the atom. If the Z group is a nitrogen, that's a electronegative element, but it's not the most electronegative element that we can think of. So, H on a carbon that's attached to a nitrogen might be like in the 2.5 region. Oxygen is a powerful electronegative group, and if it's an oxygen here, that H might be closer to 4 parts per million, for example. So knowing when you see something at 3.5 or 4, think, oh, maybe that's a proton on a carbon that's attached to an oxygen. Then as we get over to the other side of the chart, the chemical shifts get even higher. And it's an interesting thing, when a proton is on a multiple bond, like on a carbon-carbon double bond, on an aromatic ring, on an aldehyde, or near a carboxylic acid, it has a really big chemical shift. We're going to see alkenes, carbon-carbon double bonds. The H's attached to those are typically 4.5 to 6, right in the middle of the spectrum almost. Aromatic rings appear pretty far to the left. They're around 6.5 to 8, usually around 7 on average. Aldehydes are really high. They're 9 to 10. They're on the far left side. That specific proton, because it's attached to a double bond and near the electronegative oxygen, it's really de-shielded. It has a high chemical shift. And then carboxylic acids are so de-shielded that they're usually off scale, and you have to have like a little inset that says, oh, by the way, there's a signal that's off scale, and it appears at 10 to 12, even I've seen them at 15 even. They really have very high chemical shifts, because that's a very electron poor proton right there. And then you have these OHs and NHs of other types are kind of wild cards. An OH and an NH, the table lists 1 to 5. They can appear all over the place. They're highly influenced by concentration, especially hydrogen bonding. So they're kind of variable in their chemical shift, so we have to be a bit flexible about where we expect them to be. So like I said, don't try to memorize this, but definitely have this in front of you when you're looking at an NMR spectrum and trying to digest it and figure out, what is it telling me? Why are peaks where they are? And what is this peak telling me? What kind of proton might this be? As long as we're talking about chemical shifts, I'm going to tell you why protons on a benzene ring are so far downfield. Why are they so high in chemical shift? There isn't an electronegative element in a benzene ring that causes it to be that far downfield, but it's a different effect. And this is some images out of the textbook that are explaining what's going on there. So it turns out that multiple bonds generate their own magnetic fields that can either shield or de-shield. In other words, they have a magnetic moment of their own that can either point with the applied field or can oppose it, depending on what part of the molecule, where it is. So in a benzene ring, this is a picture of a benzene ring. These are the 6 carbons of a benzene ring. And then the overlapping p orbitals create kind of a donut of electron density above the plane of the carbons and below the plane of the carbons. So these two donuts of electron density in a magnetic field exhibit a circular current, and that generates its own magnetic field. And it happens to be that these yellow arrows are showing the direction that induced magnetic field points. In other words, the magnetic field that comes from these donuts of circulating electrons in the benzene point either against the external magnetic field in the center of the ring, but on the outside of the ring, where the H's live, the yellow arrows are pointing in the same direction as the big arrow. So this proton feels the external magnetic field and it feels the magnetic field of the ring current. That's what all of this text is saying. So this one gets an extra big energy gap, because it's got the external magnetic field and then it's got this applied or induced magnetic field that's making its energy gap even bigger. So these have really high chemical shifts because they're in a region of space where the magnetic field is really large. So in other words, bottom line is protons on benzene ring, high chemical shift, much higher than you'd expect for a molecule that doesn't have any electronegative elements. All right. Carbon-carbon double bonds are the same way. This is a molecular orbital picture of a carbon-carbon double bond. There's the sigma bond here that's between the two carbons. Then there's the pi bond. The pi bond is overlapping p orbitals, and that's illustrated by these blue ovals here. That represents the overlapping p orbitals, and there's a pair of electrons that are shared in these overlapping orbitals. And those electrons can kind of circulate too, and they generate their own magnetic field, which points in the direction of the small dashed arrows. And in the region of protons on a double bond, the induced magnetic field, the small arrow, overlaps with the big arrow. They point in the same direction. So again, these protons on a carbon-carbon double bond feel an extra magnetic field, and they get more chemical shift because their energy gap between alpha and beta spin states is bigger. In a triple bond, the situation's a little different. It's a barrel of electron density that is formed from the two overlapping sets of p orbitals, and that has electron circulation and its own induced magnetic field that points against the external field. So protons on a triple bond are actually shielded by that induced magnetic field. So that's why these show up at 2.5. So this proton is shielded because in its vicinity, the dashed arrows are pointing in the opposite direction of the big arrow. So the dashed arrow cancels out the big arrow to some small extent. So these are shielded. So that gives you at least a theoretical explanation for why the chemical shifts are the way that they are. We're going to dig more into chemical shift when we come back next time, and we're going to hit number of signals really hard. We're going to talk about how many different kinds of protons are in a molecule, because this is the next big thing to understand is if you've got a molecule, how many signals would you expect to see? And the idea is that in many molecules, the protons, you have a lot of protons, but some of the protons are the same. Protons in the same chemical environment give the same signal, and protons in different chemical environments give different signals. So we're going to look at a lot of symmetry arguments to describe in the next lecture why is it that some protons are the same and others are different. Just ways to figure that out. But this is an introduction to NMR and some chemical shift ideas. Different protons have different chemical shifts depending on where they are, what they're near in terms of functional groups. So we'll pick it up again next time, talk more about NMR. So have a good day.